Okay, so welcome back to this next video in which we are discussing the Sylow theorems. Okay, right, so we've now succeeded in proving the first part of the third Sylow theorem. Okay, and the first part of the third Sylow theorem was that the number of Sylow P subgroups in the group capital G divided this number n, which remember was the portion of the order of the group that was left over after you'd pulled out the highest power of p you could from the order of the group. Okay, right, now what we want to turn our attention onto is part 2 of the third Sylow theorem, which tells us that the number of Sylow P subgroups in the group capital G is actually congruent to 1 modulo p. Okay, which means that it is equal to some multiple of the prime p, okay, some positive integer multiple of p, so some natural number times p plus 1, so it's 1 greater than some multiple of p. Okay, right, so how are we going to prove this? Well, we're going to prove it with a continuation of the method which we use to prove the part 1 of the third Sylow theorem. Okay, so we're going to use this same group action that we've been using previously, where the elements of the group were acting on the elements of the set of Sylow P subgroups. And I'll try and just get back the pick at on this side. Okay, so here is my picture of this group action. Here's the group action composition table. Okay, and I've got all of the elements of the Sylow P subgroup up here, or rather the set of all Sylow P subgroups in G up here. Okay, and the elements of the group can act on the elements of this set of all Sylow P subgroups of G, and they send the Sylow P subgroups onto what the Sylow P subgroup is conjugated by the element little g. Okay, and we've seen that that is a group action. Okay, so what we're going to now do to try and prove the second part of Sylow's third theorem is we're going to restrict that group action down. Okay, and we're going to restrict it down to one of the Sylow P subgroups. And here, to do this, we're going to need to change our notation a little bit. Okay, so what I now want to give you is a new bit of notation. Okay, so we are now going to actually name the elements of this set of Sylow P subgroups of the group capital G here. So remember, this is the set of all Sylow P subgroups of the group capital G. So I'll explicitly now for the first time actually write this out. So this will be full of Sylow P subgroups. So we'll have the first Sylow P subgroup here, then we'll have the second Sylow P subgroup here, and it will go on and on all the way up to the nth Sylow P subgroup. Remember, NP is the number of Sylow P subgroups, the order of this set basically. So here is that final one in this set. Okay, so this is the new notation that I've got now. I've explicitly now got notation for all the elements in my in my set of all Sylow P subgroups of G. Okay, right. So what I'm now going to do is take one of these arbitrary Sylow P subgroups from this set. Okay, and we might as well take the one that I've now called H1. Okay, but you could have taken any of them. The argument will still work for any of them. You just need to take one. To prove this fact, we just need to use one of them. Okay, so we'll use this one H1. Okay, and what we're going to do is we're going to restrict that group action that we had previously by the entire group capital G on this set of Sylow P subgroups of capital G, and we're going to restrict it down now so that it's just capital H1's elements acting on this set of Sylow P subgroups of G. Okay, so we're going to restrict the group action down, but the entries of the group action composition table are going to remain exactly the same for the ones that remain. Okay, so here now is our Sylow P subgroup of capital G. Okay, so we've got rid of loads of rows in the group action composition table, and now we've just got the elements of the group that are actually in this Sylow P subgroup here, capital H1. Okay, but we won't have reduced the number of columns here. All of the Sylow P subgroups of G will still have a column dedicated to them. This bit hasn't changed. Okay, so I'll colour this portion once again in turquoise here. Okay, right, and we will leave the composition exactly the same as well. So if you've got any element of this Sylow P subgroup, capital H1, okay, so we'll say little h here, and you want to act it on a Sylow P subgroup, which we'll call hi, okay, so where I is equal to 1, 2, all the way up to np, okay, the answer is just going to be this Sylow P subgroup conjugated by the element little h, okay, so little h, little capital Hi, little h inverse here, okay, so the answers for the compositions that are left over in this restricted group action composition table are going to be exactly the same as they were in the larger group action composition table. Okay, so we've just restricted the group action down a little bit. Okay, and this will still obey the axioms of a group action that it did when it was part of that larger group action composition table. So we've still got a nice group action here. Okay, right. So what we now want to do then is we want to consider what are the orbits now of this group action. Okay, so we want to split the set of all Sylow P subgroups of capital G up into orbits for this group action. Previously, when we had the entire group here, it was a transitive group action, so there was only one great big orbit of this set of all Sylow P subgroups. Now we've restricted our attention down hugely, and it is no longer going to be transitive, okay? And we're going to be able to arrive at this part 2 of the third Sylow theorem by looking at the orbits of this restricted group action here. Okay, so once again I'll draw out my set here. So here is the set of all Sylow P subgroups of G, and we're now going to use this restricted group action to partition it up into subsets. Okay, right. So firstly, let me just convince you that this is definitely not transitive anymore. And the reason I can instantly say that it's not transitive is let's consider what orbit the Sylow P subgroup capital H1 itself is actually going to be in. Okay, so it's certainly an element of this set of Sylow P subgroups of G. Okay, so let's ask what orbit is it going to be in? Okay, well, its orbit, the orbit of capital H1 here, okay, is going to be all things that H1 can be sent onto by elements of the group, but the elements of the group are capital H1 in this case. Okay, so we're asking what Sylow P subgroups can we take capital H1 onto by conjugating it by elements of capital H1. Okay, and I should just say capital little h here is an element of capital H1. Okay, so and that's getting a bit confusing because the i's look like ones. Let's turn the I into R. Okay, so R again is something from 1 to all the way up to NP. I just don't want the 1 and the I to get confused, and they will end up getting confused if I'm not careful. Okay, I'm going to need this notation later on as well, so I'll fix it now, basically. Okay, so basically when we conjugate capital H1 by any element of the group capital H1 itself, we're not going to get any new Sylow P subgroup, okay, because what you have to do is go through and conjugate all the elements of capital H1 by this element little h, which is in capital H1, and when you do that, all of the answers will be back in capital H1 because capital H1 is a subgroup and therefore closed under composition. So basically my lesson here is capital H1 will appear in an orbit by itself always. Okay, so capital H1 here, this Sylow P subgroup that we use to restrict the group action down to, it will always be in an orbit by itself. So instantly I can say then that this group action is not transitive because look, here is this Sylow P subgroup on its own. And unless, of course, the Sylow P subgroups, the set of all Sylow P subgroups only contains H1, then it won't be transitive. But if you have a set that's larger than 1, then it's not going to be transitive. Okay, right, so what I can now do is use this to prove part 2 of the third Sylow theorem. Okay, and the way that I can use it to prove part 2 of the third Sylow theorem is I can say that the order of this set of all Sylow P subgroups of G, okay, which is my little MP here, is just going to be the sum of the orders of all of these orbits. Okay, so I just need to add up the sums of all of these orbits. Okay, now if I wanted to prove that it is congruent to 1 modulo p, i.e. it is some multiple of p plus 1, then wouldn't that be the case if all of the other orbits here, so let me now draw on the other orbits here, if all of these other orbits were multiples of p, then wouldn't it be now the case that the order of this set of all Sylow p subgroups of G would indeed be equal to a multiple of p plus 1, because I'd have to add up all the orders of all the other orbits, so all of these portions, and if they were all multiples of p, then the whole lot of them added together would also be a multiple of p. Okay, so I'd end up with a multiple of p from there, plus the 1 here, okay, which is the orbit containing my h1. Okay, so if I could prove that all these other orbits in this set of Sylow p subgroups in G had orders that were multiples of p, then I'd be in business. I'd have proven this. Okay, so let's explore this in a little bit more detail. So let's use the orbit stabilizer theorem to gain some more insight into the order of an orbit. So let's now take the order, let's take an orbit of some arbitrary Sylow p subgroup, which I'll call HR. Okay, so let's consider what the orbit of this Sylow p subgroup HR, and note R is something, some number from 1 to np here. Okay, now we're not really interested in 1 because 1's already over here, but some other entry from this set of Sylow p subgroups of G. Okay, right, now let's use the orbit stabilizer theorem to gain some insight about the order of this orbit. Okay, so what we know from the orbit stabilizer theorem is that the order of this Sylow p subgroup, the order of this orbit of this Sylow p subgroup, capital HR, is going to be equal to the order of the group, okay, and whoops, I've made a terrible mistake. The order of the group in this case is not G, because that's not the group that we're using for the group action. The group that we're using for the group action is capital H1. Okay, so the order of H1 divided by the order of the stabilizer of this Sylow p subgroup, capital HR, in the group H1, okay, and this is where the notation looks awful, okay. It's going to be, here's my group H1, and then I need to subscript it, capital HR. So this is the stabilizer of this Sylow p subgroup, capital HR, in the group capital H1. Okay, right. So here is my equation then for the order of the orbit of this Sylow p subgroup, capital HR. Okay, now what I can instantly do is replace the order of this group, capital H1 here, with p to the power of alpha, because it, remember, was a Sylow p subgroup. Okay, so I don't really care what the order of this is, okay, because I've got now a very valuable piece of information just from this. This tells me a lot about the order of the orbit of this Sylow p subgroup, capital HR. It tells me that this must either equal 1 or it must be some power of p, okay, because whatever this is, it will just cancel a bunch of the powers of p. Now the biggest possible situation is that this is equal to p to the power of alpha, okay, and then it will completely cancel here and you'll end up with this equaling 1. But if this is some lower power of p, then you'll end up with this having to be a power of p. So basically there are only two options for the order of the orbit of a Sylow p subgroup, capital HR. It's either equal to 1 or it's some power of p, basically, okay, and beta here is between 1 and alpha, basically. It varies between 1 and alpha. Okay, right, so that's now a very valuable piece of information, because that tells me that all of these orbits that I'm going to split my set of all Sylow p subgroups of G down into have to either have order 1 or they're going to be a power of the prime p. Okay, now, if I could prove that this orbit here, the orbit containing capital H1, was the only orbit that contains one element, okay, and all of the other orbits can't contain just one element, then all of the other orbits would have to have an order that was a power of p, and that if they're a power of p, then they certainly are a multiple of p. So when I add them all together, when I add all their orders together, I will end up with a multiple of p. Okay, so in this equation, I will add up all of these orbits' orders, to get a multiple of p, plus this final one, which will be 1, and that will then tell me that the number of Sylow P subgroups in G will be equal to some multiple of p plus 1, i.e. it will be congruent to 1 modulo p. So what I have reduced this problem into is just showing that there cannot be any other Sylow P subgroup that is in an orbit on its own, basically. Only capital H1, the Sylow P subgroup which we were actually using to act on the group, act on the set of all Sylow P subgroups of G, only that one can actually be in an orbit on its own. All the others cannot be in an orbit on their own. Okay, so that's the final thing that I need to prove in order to prove part 2 of Sylow's third theorem. Okay, so how am I going to do this? Well, I'm going to do this by a proof by contradiction. Okay, so what we're going to do is we're going to assume the exact opposite of what we want to prove. Okay, and I'll just bring up back my picture. So we're going to assume that this Sylow P subgroup, capital HR, is actually in an orbit of just one element, basically. Okay, so we're now going to assume that the order of this orbit containing the Sylow P subgroup, capital HR, where R is some number from 2 to NP, basically. So it's some Sylow P subgroup apart from capital H1. We're now going to assume that this is equal to 1. Okay, and we're going to arrive at a contradiction that will show us that no other Sylow P subgroup can possibly exist in an orbit of order 1, basically. Okay, so how are we going to do that then? Okay, well, let's instantly think about what this actually means. Okay, so if this Sylow P subgroup, capital HR, is in an orbit on its own, then that means that when I act all the elements of the group, capital H1, the Sylow P subgroup, capital H1, on capital HR, they do nothing, basically. They're effectless. Okay, so this means that for all, what shall I call it, little h, which is an element of capital H1, so all elements of the first Sylow P subgroup here, okay, I can use them to conjugate capital HR, so A, HR, H inverse is equal to capital HR, okay, so they all have absolutely no effect when they conjugate capital HR. Stated another way, this means that for all H bar, which is an element of capital HR, and you can now see why I switched my notation from capital HI to capital HR, because if I was still using I, it would look very similar to capital H1 here, so that's why I switched the notation when I was early in. Okay, so for all little h bar is an element of capital HR, it needs to be the case that H bar, H inverse, is some other element of capital HR. Okay, so whatever little h you pick from this first Sylow P subgroup, capital H1, and whatever h bar you pick from my Sylow P subgroup, capital HR, it's the case that when I conjugate little h bar by little h, I end up with some other answer that is back within my Sylow P subgroup, capital HR. Now, what does that mean about all of these elements in this Sylow P subgroup, capital H1? Well, it means that they are all contained, okay, so the entire subgroup here is contained within the normalizer of this Sylow P subgroup, capital HR in G. Because let me just remind you of the definition of the normalizer of the Sylow P subgroup, capital HR in the group capital G. So now I'll finally go on to my other piece of paper and I'll try and get them both in here. Okay, so the definition, of the normalizer of capital HR in G, okay, is all elements of the group, so all little g is an element of the group capital G, such that when I use little g to conjugate any element of my subgroup capital HR, okay, so I'll again call that h bar, so GH, G inverse is an element of capital HR for all h bar is an element of capital HR, and that's exactly what I've just said about all of these elements of capital H1. All of them will conjugate absolutely all of the elements of capital HR to give back another element in capital HR. Okay, so that now tells me that this this Sylow P subgroup, capital H1, is completely contained within the normalizer of capital HR in the group capital G. Okay, now what we will also know is that all of the elements of capital HR are completely contained within the normalizer of HR in G. Now that's true for any subgroup, so whenever you construct the normalizer of a subgroup of the group capital G, you'll always find all of the elements of the subgroup itself are in the normalizer, basically. Okay, and that's because any element that's actually in this subgroup will be able to conjugate any other element that's in the subgroup to get another element in the subgroup. Okay, so let's draw a picture of this then now. Okay, and we'll realise why this produces a contradiction in just a moment. Okay, so here is our entire group, capital G. Okay, and I'm just wondering whether I can get rid of this yet. The only thing that we're going to need is that H1 is also completely contained within the normalizer of HR and G. Okay, so that's just this line here. So I'll just bring those two down here. Okay, and then I can get rid of this piece of paper here and stabilise this piece of paper here so to stop it falling off the edge. Okay, right. So here is my group, which I'll colour in green here. So here's my group, capital G. Okay, and now let's mark on my subgroup, capital HR, firstly. So here is capital HR. Okay, this Sylow P subgroup, which we assumed initially was in an orbit of size 1. Okay, then we'll mark on the subgroup capital H1 here. So here is capital H1, and they'll have a non-empty intersection because they're both subgroups, so they must both contain the identity element of the group capital G. Okay, so here's capital H1. Okay, and the picture now is that what I've done is I've constructed the normalizer of HR and G, and that has to completely contain H1. So we'll say that the normalizer then is this square here. Okay, so why is this going to lead to a contradiction? Okay, well it is, but to see why we need to study a few more little facts. Okay, so firstly, let's just consider what is going to be the order of the normalizer of HR and G. Okay, so let's just consider the order of the normalizer of HR and G. Okay, well the key thing is, oh, in fact there's something I need to tell you before that. Okay, so we've just shown that these subgroups, H1 and HR, are subsets of the normalizer of HR in G. Now the normalizer of HR in G, the normalizer of any subset in a group G, is always a subgroup. That's something we prove in the video on centralizers and normalizers. Okay, so that means that HR and H1, these are both subgroups of the normalizer of HR and G. Okay, so we can change these into stronger conditions that they are subgroups of the normalizer of HR in G. Okay, again, the picture captures that fact. Okay, right. Now what we can do is, if we're trying to work out the order of the normalizer of HR in G, we can apply the Granger's theorem. Now the Granger's theorem says that the order of a subgroup must divide the order of the group. Both of these subgroups have order p to the power of alpha. Okay, so that means that the order of this larger group here must be equal to some multiple of p to the power of alpha. Now it itself is a subgroup in the group capital G, so the normalizer of HR in G is a subgroup of capital G, so its order must divide the order of the group, and the order of the group, remember, is p to the power of alpha times m. So we can say that the order of the normalizer of HR in G will be p to the power of alpha times m bar, okay, where m bar is again some portion of m potentially here. Okay, now m bar could be 1, okay, but the important fact here is that you have to have that full p to the power of alpha there. Okay, right, so now what we're going to do is we can say, okay, well, H1 and HR then, okay, these are Sylow P subgroups in the normalizer of HR in G. So they are elements of the set of Sylow P subgroups of the normalizer of HR in G, okay, because they are subgroups of this group, and this group has order p to the power of alpha times m bar, so the highest power of p that it has is p to the power of alpha. These subgroups both have order p to the power of alpha, okay, therefore they must be Sylow p subgroups in the group which is the normalizer of HR in G. Okay, and we're very close to our contradiction, I promise. Okay, so what does it mean if these two are both Sylow p subgroups of the normalizer of HR in G? Well, what do we know about Sylow p subgroups in some group? That they have to be conjugate to one another in that subgroup, or in that group rather. Okay, so what we can do is apply that corollary of Sylow's second theorem, okay, and say there must exist, let's say, some little a, which is an element of the normalizer of HR in G, okay, such that if I conjugate little hr by little a, okay, I end up with capital H1 basically. Okay, that's the corollary of the second Sylow theorem. Okay, now why is there a problem with that statement? Okay, well the problem with that statement is that all the elements of the normalizer of HR in G are defined to conjugate any element of the subgroup capital HR and send it onto another element in capital HR. Here is the definition of the normalizer of HR in G. It's all elements of the group capital G such that when they conjugate any element of the subgroup capital HR, you get another element of capital HR. Okay, so when we conjugate all of the elements of the subgroup capital HR by little a, okay, which is an element of the normalizer of HR in G, we must get elements of capital HR back again. So the answer to this is capital HR. Okay, so you can never get it going on to capital H1. So that's a contradiction. Okay, that will break the corollary of the second Sylow theorem. Okay, so we have to go all the way back to a point where we made an assumption that we didn't know was true, and that was the assumption that capital HR could exist in an orbit on its own. Okay, so this contradiction that we've found here, okay, this then contradicts the fact that capital HR could have existed in a orbit on its own, okay, because capital H1 cannot exist in the normalizer of capital HR in G, basically. Okay, right, so that now means, going all the way back, that we now know that this partition that we have of the set of all Sylow p subgroups of the group capital G, this will contain one orbit of size 1, and then all the other orbits must have some positive power of p as their order, okay, and therefore when we add up these orders of all those other orbits in red here, we will get a multiple of p overall, and then we'll add this 1 onto it, and therefore the order of the set of all Sylow p subgroups of the group capital G must be some multiple of p plus 1, i.e. it must be congruent to 1 modulo p. So we now have proven the third Sylow theorem, and with that we will conclude this discussion of the Sylow theorems.